Hello everyone, I am Anita, working as an assistant professor in the Department of ECE, SJBIT Institute of Technology. Today we are going to learn about Instrumentation Amplifier, which is the first experiment in ACLIC lab 4th semester according to VTU syllabus. Instrumentation Amplifier, as the name itself indicates, which is used in industries. The main application is, suppose in industry or consumer applications, we'll be measuring few physical quantities like temperature, humidity. Those quantities has to be converted or has to be controlled. While converting from physical quantities, we'll make use a transducer. The transducer will convert the physical quantity into its equivalent analog voltage. That analog voltage that we will get is very low amplitude, which has to be used for further processing. So for further processing, that means in order to amplify that very low input signal, we'll make use an instrumentation amplifier. Main purpose of instrumentation amplifier is to enhance the very low amplitude signal. That's about the theory. Coming to the experiment, which is conducted by using a operational amplifier. Operational amplifier, here we are making use of a MUA741 op-amp or LM series, LM741 op-amp. As you can observe in the op-amp, which is a 8-pin IC, in that 2 pins are dedicated for input, non-inverting and inverting, second pin and third pin. 2 will be given for power supply, plus VCC minus VEE. 1 is output. And pin diagram, if you can observe, 2 and 3 inputs, plus or minus VCC, power supply, and 8th pin is no connection. Offset null, indicating offset DC offset voltages. If we want to vary, we can vary by connecting a resistor between these 2 points. Output is taken at pin number 6. So this IC will be making use to conduct an instrumentation amplifier, which uses basically 3 operational amplifiers. Main features as we require for industrial or consumer applications. For an instrumentation amplifier, here it includes, it has to have a very high gain accuracy and high CMRR. CMRR indicating common mode rejection ratio, that means noise signals which has to be eliminated. So which is a ratio of differential gain to the common mode gain, which must be very high for an instrumentation amplifier, and high gain stability we need, and low DC offset. Offset is the one, even if you want given a power supply, we'll get an output voltage which has to be eliminated by connecting offset null, that is by connecting a resistors. So low DC offset we need, and low output impedance, high input impedance we need. So these are the requirements for an instrumentation amplifier, which can be achieved by using a normal differential amplifier. Problem with a differential amplifier is it consists of mainly 2 stages. Instrumentation amplifier, first one is a differential input output stage. Second stage is a differential amplifier. As we know, in a differential amplifier, the input impedance of the differential amplifier is reduced. That's the reason why we go for stage 1. In that stage 1, we'll be making use of non-inverting amplifiers, 2 non-inverting amplifiers. This is a non-inverting, first one, second one, 2 non-inverting amplifiers, and which is given as an input to the stage 2, which is a difference amplifier. So what we are supposed to do is, you need to amplify the difference between the 2 input signals. So you need to give 2 input signals, 2 inputs to be considered, one from one signal generator, another one from another signal generator, which is given to 2 non-inverting amplifiers, and the output of that must be given to a difference amplifier. Why we are using 2 stages means, the first stage, whatever we use, the main drawback of that second stage difference amplifier is input impedance is reduced. That drawback is eliminated in first stage. So coming to the second one, we are making use of a difference amplifier. The main drawback of that is common mode gain. As we know, for instrumentation amplifier, we need high CMRR. For that, you need to have a common mode gain as 0. So in order to have a common mode gain as 0, if I make use a difference amplifier, we'll get a common mode gain approximately 0. Problem with this stage 1 is common mode gain is unity. That is eliminated in stage 2. So each stage will have its own advantage and disadvantage. To combining stage 1 and stage 2, we can attain the requirements of an instrumentation amplifier. So this is a overall circuit diagram. Here you can observe first stage, differential input output amplifier consisting of two op-amps configured as a non-inverting amplifier. How we can identify means input given to plus terminal, even here input given to plus terminal, feedback given to inverting terminal, which is a second pin. Then output of this you will get difference between two input signals, which is given to a difference amplifier. Second one is a difference amplifier. So final output is an amplified version of the difference of two input signals. The same thing, the design of that, if you observe, we have stage 1 and stage 2. Stage 1, overall gain of the stage 1 is V0 by difference input, V1 minus V2, two inputs difference, so which is 2R1 plus R2 by R2, that means this is 2R1 by R1 plus R2. To have a gain of 21, they are chosen the values of R1 and R3. Coming to stage 2, similarly stage 2 which has to be designed considering the condition R4 must be same as R5, R6 must be same as R7. That is the case of difference amplifier design. So they are chosen here the gain of a second stage as unity. So all the resistors are chosen equal 10 kilo ohms. So with that gain of the second stage you will get as 1. Gain of the first stage we get as 21. Overall gain, if I want to calculate, which is first stage gain multiplied with second stage, so you will get 21. So now we need to consider for different inputs variations how you will get a output voltage. So for that you can observe three operational amplifiers. First op-amp, second op-amp configured as non-inverting, third one, last one is a difference amplifier. These are all 10 kilo ohm resistors. 10 kilo ohm resistors. Then in the first stage we will be making use one resistor which is R2 as a potentiometer. This is a pot, 5 kilo ohm pot or 1 kilo ohm pot potentiometer you can make use. By adjusting this you can vary the amplitude. By adjusting this you can vary the gain of the first stage. So AV1 if I want to vary, you can vary the resistor R1, R2, 1 kilo ohm. If I vary, gain of the first stage varies, overall gain of the circuit will be varied. Then coming to the input, you can observe two inputs we are supposed to give, difference of those two must be amplified and you need to get output as a 21 times. Let us consider this is a first signal generator which is used to generate a signal of sine wave. Here we are making use of a 10 millivolts sine wave 1 kilohertz frequency. So 1 kilohertz frequency you set, then sine wave from the function generator you opt for the sine wave, then 1 kilohertz amplitude that you need to set as a 10 milli, because in industrial applications, as I said, the physical quantity once if you convert through a transducer you will get a very low amplitude, which is in millivolts. Sometimes even in industrial applications you will get in microvolts or nanovolts range. That I need to enhance up to volts. Lab purpose, the signal generator which we will make use will not give a microvolts range, we will get only millivolts range. So first let us consider millivolt range input signal. So first input which I am giving is a 10 millivolts. So connect to first signal generator, this is a first signal generator, 10 millivolts. In order to get 10 millivolts range, keep in mind you need to apply attenuation, 20 dB, 40 dB which they had provided to give attenuation. A very low amplitude signal if I want to generate, give attenuation by using these two, 20 dB and 40 dB accordingly. Signal generator directly connect to CRO and measure for 10 millivolt signal. So one box along y-axis you need to measure for amplitude into 10 millivolts range, 10 millivolts first signal. This is a second input which we are giving from second signal generator, same 1 kilohertz sine wave, and apply attenuation, give an input of 50 millivolts. So directly connect signal generator to CRO and measure 50 millivolts whether it is there or not. Then connect to the circuit, second input. Input is given to second IC pin number 3. First input is given to pin number 3 of first IC. This is the first IC, second one, third one. Then connect final one first IC 6th pin output which is connected through a resistor to second pin. Similarly, second IC 6th pin is connected to third pin. Then final output is taken at pin number 6 of third IC, so which is connected to CRO. Amplified version of the signal you need to get. A sine wave signal amplification, how you can determine means measure the amplitude. So here we are getting 0.8 volts which is kept in 1 volt range. So 0.8 into 1, 0.8 volts. According to theory, we are given 10 millivolts one input, 50 millivolts another input. The difference is 40 millivolts. Gain of the circuit which we had chosen is 21. So 21 into 40 millivolts which gives to 0.8 volts. So even after connection we are getting the same. So 0.8 volts we are getting. This is about the instrumentation amplifier. The expected lab Viva questions are, you need to know about the features of instrumentation amplifier and the drawback of each and every stage. Why we are connecting two different stages in instrumentation amplifier and how to design the resistor values for the given requirement. Thank you.